Hi everyone, this is the video for our ENG 3001 Mathematics Engineering assignment. Our topic is thermodynamics. Our group members are Ahmad Wafiuddin Hakim bin Yaakob, Muhammad Amirul Irfan bin Muhammad, Muhammad Ikram Saif bin Latif, and me, Wing En. The introduction of our assignment will start by the thermodynamics definition. Thermodynamics is the science of heat, work, temperature, and energy, and how they affect matter and each other. One of the process under thermodynamics is isobaric process. An isobaric process is a thermodynamic process in which the pressure remains constant, which means that when the temperature changes, the pressure will remain unchanged. This can be explained by the principle of conservation of energy, which also similar to the first law of thermodynamics. First law of thermodynamics states that energy is conserved. It can only be transferred from one form to another form, but cannot be created or destroyed. The formula for first law of thermodynamics can be derived mathematically. By using this formula, Q equal to W plus delta U, where Q is the quantity of heat supplied onto the system, W is the work done onto the system, and delta U is the change in internal energy of the enclosed system. And in this case, sign convention is important. The formula for isobaric process can also be derived by using the formula W equals to integrate of P dV. And finally, we will get the result that work done is equal to P delta V. This is another question that will be done by us.
So I'm going to present to you about the assumption. So for that, two closed systems are under consideration as shown in the schematic. And then the second one, the only significant heat transfer is from the resistor to the air, during which the air expands slowly and its pressure remains constant. And then there is no net change in kinetic energy. The change in potential energy of the air is negligible, and since the piston material is a good insulator, the internal energy of the piston is not affected by the heat transfer. And then friction between the piston and cylinder wall is negligible. And lastly, the acceleration of the gravity is constant, which is G equals to 9.8 meter per second square.
So we're going to present the solution for this thermodynamic question. And from the question, we can notice that this is the vertical piston cylinder, and from the solution given, we can see the data given. So for the first data, we can see the atmosphere exert pressure is 101.3 kPa, and then mass of piston is 4.5 ton 10 power of 4 gram, and the area of piston is 0.09290 meter square. And then you can see the mass of the air is 0.27 kilogram, and change in volume of the air is 45.31 liter. And we can see the initial temperature. The initial temperature is 25 degrees Celsius, and the final temperature is 83.4 degrees Celsius. And I'm gonna explain about the step 1. So we're going to the step 1. So step 1, we're taking the air as the system, the energy balance reduced. With assumption 3, we can take the assumption from the previous part. So for the assumption 3, so solving the change of internal energy of the air. So we can use the formula given. So the formula is in change kinetic energy plus change potential energy plus change initial energy equals to the heat transfer minus work done. Using the assumption 3, we can cancel out change kinetic energy and change potential energy. So the final equation that we get is change of internal energy of the air equals to the heat transfer minus work done.
For the second step, from this system, work is done by the force of the pressure, which is P, acting on the bottom of the piston as the air expands. So we assume that the pressure is constant, and then we can come up with an equation such that W equals to the integration of V1 to V2, P, which is pressure, and then dV, which is the integration of volume, equals to P, which is pressure, and then bracket V2 minus V1, which V2 stands for final volume of air, and then V1 is the initial volume of air. So by this equation, we can apply it by using the function method to find W. So we assume that W equals to Fx, and then we are able to come up with an equation which is Fx equals to P, pressure, bracket V2 minus V1.
Step 3 is to determine the pressure P. So we use a force balance on the slowly moving frictionless piston. The upward force exerted by the air on the bottom of the piston equals the weight of the piston plus the downward force of the atmosphere acting on top of the piston. This can be expressed by the equation below.
So for the stats 4, we already know the value mass of piston and the value area of piston. So to get the value of pressure, we need to substitute all the value into the equation P equal to M piston multiplied with gravity over area of piston plus pressure of ATM. So in order to get the final answer in Newton over M square, we need to multiply our last answer with Newton over M square over 10 to the power of 3 kilopascal to get the last answer 4.75 multiplied with 10 to the power of 3 Newton over M square. So after we get the value of pressure, we need to substitute again that value into equation Fs equal to P multiplied with difference in volume. So again, to get our final answer in kilojoule, we need to multiply our last answer with 0.028317 m cubed over 28.317 L and multiply again with 1 kg over 10 to the power of 3 Newton meter to get our value of function 0.2152 kilojoule. So for the step 5, to determine the heat transfer from the resistor to the air with assumption 3 to find Q. Heat transfer can be expressed as Q equal to mass of air multiplied with specific heat of air and multiplied with difference in temperature. So by using the application of function to find Q, let Hs equal to Q. So the equation of Hs is Hs equal to mass of air multiplied with specific heat of air and multiply again with difference in temperature. So substitute all the value into the equation and we get the final answer 16.20 kilojoule. So for the information, to get the final answer in kilojoule, we need to multiply our answer with 1000 gram over 1 kilogram and multiply again with 1 kilojoule over 10 to the power of 3 joule.
So for the last step is step 6 to determine the change of initial energy of the air. So we get all the information. So the change of internal energy equals to Q minus W. So the Q is the heat transfer. The heat transfer is 60.20 kilojoule and minus work done, and the work done is 0.2152 kilojoule, and the final answer is 15.98 kilojoule. And that's all for us. Thank you.